Hello viewers, I am Dr. Mala Das Sharma, retired professor of St. Pius X Degree and PG College for Women. Welcome to my channel Chemphilic. Let's start the 24th episode of Teaching Chemistry through Riddle. Do watch the video till the end and join me in this program by answering the viewer's question. So we start riddle number 24. X is a fragmentation process associated with a technique used for identification of organic compounds. The application of the external magnetic field is the primary requirement to execute this technique. Because of X, expected single outline of a particular isotope is observed as multiplet in the above-mentioned identification technique. The number of constituent lines of a multiplet can be calculated by a formula that contains the number of same isotopes present in the adjacent positions. So, this is riddle number 24. Now, let's see the question. Primary question is, what is X? The answer is splitting of NMR signals or spin-spin coupling. Second part of the primary question is, name the identification technique referred in the riddle. Answer is proton NMR. Now the other questions associated with these riddles are, second question, how the neighboring isotopes are responsible for the fragmentation. Third question, what is the formula that gives the number of fragmented lines? Fourth question, what will be the probable combination of the alignment of two same neighboring isotopes with the direction of the applied magnetic field? Now, in this video, we'll start with the equivalent and non-equivalent protons. Let's see. Now see, in this molecule, these three protons attached with this carbon atom, they are in one electronic environment. Similarly, these two protons, which is attached to this carbon atom, and this carbon atom is attached to this oxygen atom, they are in one same electronic environment, which is different from this proton, that electronic environment. Similarly, these three protons, which is attached to this carbon atom, they are also in the same electronic environment. Now, these protons, these three protons, which are in the same electronic environment, are equivalent protons. Similarly, these two protons are equivalent protons. Similarly, these three protons are equivalent protons. But these three protons and these two protons are not in the same electronic environment. So, they are non-equivalent protons. Similarly, these two protons and these three protons are non-equivalent. And these three protons and these three protons are non-equivalent. And equivalent protons gives the NMR signal in the same position, and non-equivalent protons will give them an NMR signal in different position. So, equivalent proton is the set of protons with identical electronic environment gives NMR absorption signal at the same position. Non-equivalent protons with different electronic environment give NMR signals at different position. Now coming to peak area and proton counting. See, so for a particular proton or set of equivalent protons, we'll get the NMR signal, that NMR peak. It may be a single peak or it may be a multiplet where a number of peaks are closely spaced. In most of the cases, we will get the multiplet. That is the splitting of these spectral lines. I will discuss it now. So, whatever it is, if it is a multiplet or single peak, area under this peak gives the relative number of protons giving rise to that signal. And the computer will calculate the area of each peak and representing that area with this step curve. And if the area is more, that means more number of protons are absorbing at this position or at this magnetic field. So, greater number of protons which flip over a particular frequency, greater is the energy absorbed and greater is the area under the absorption peak. Now, spin-spin splitting, spin-spin coupling. What is that? Look at this molecule. This is the hydrogen atom Ha, which is attached to this carbon atom, and the adjacent carbon atom or the neighboring carbon atom does not have any hydrogen atom. In that case, the NMR signal of this hydrogen atom will be consisting of a single peak. That means a singlet will be found. But here you see, these two equivalent hydrogen, just red color, denoted by red color, its NMR signal is splitted into two peaks, doublet. Similarly, this blue hydrogen, its NMR signal splitted into three. In this molecule, these two equivalent hydrogen, red color two equivalent hydrogen, its NMR signal splitted into three. Similarly, these two blue colored equivalent hydrogen also NMR signal splitted into three. In this molecule, these two blue colored equivalent hydrogen, its NMR signal is splitted into four, quadrant. And these three red colored equivalent hydrogen, their NMR signal splitted into three. And in this molecule, these three red colored equivalent hydrogen, NMR signal is splitted into two peaks or doublet is observed. And for this proton, blue colored proton, the NMR signal is splitted into four, quadrant. Okay. So, in most of the molecules, this NMR signal or NMR peak of a particular proton or a set of equivalent protons will be a multiplet, that means splitted into number of peaks. So, most of the cases, instead of single peak for one kind of protons, a group of peaks, multiplet is observed in the PMR, proton magnetic resonance spectrum. This is called splitting of NMR signals or spin-spin splitting. Now, look at this molecule. This is 1,1-difluoro, 2,2-difluoroethane. Okay. Now, for this carbon atom, which is attached with this carbon atom, one hydrogen atom is attached. Similarly, with this carbon atom also, one hydrogen atom is attached. Right. Now, consider this hydrogen atom. For this hydrogen atom, the adjacent hydrogen, that means hydrogen attached to the adjacent carbon atom is this hydrogen atom, which will be attached here. Now what happened? The proton, that means the spin of this proton and the spin of this neighboring proton, the couple or a coupling takes place between the spin of this proton and the adjacent proton through the intervening bonding electrons. And because of this coupling, what happened? This proton, this particular proton, or the magnetic field experienced by this particular proton will be modified by the magnetic field of this neighboring proton. How? Let's see. See what happened? If the neighboring proton's magnetic field is aligned with the applied magnetic field, then the overall field strength will increase. In that case, this proton will experience more magnetic field, so it will absorb at lower magnetic field. Or in the otherwise, this proton's magnetic field may oppose the applied magnetic field. In that case, the magnetic field strength is decreased. So when this proton experiences this magnetic field strength, that means lower magnetic field strength, it will absorb at higher field or up field. And this change of alignment is very much even. So in the molecule, same number of proton, that means this proton in the half of the molecule will experience this magnetic field. They will give the absorption peak little higher little lower magnetic field, and half of the molecule, that means this proton in half of the molecule will experience this magnetic field, that means less magnetic field, and they will absorb at little higher magnetic field or arc field. So, splitting of NMR signals is caused by spin-spin coupling, which is indirect coupling of proton spins through the intervening bonding electrons. The absorbing proton may experience, just now I explained, experience slightly higher or lower field depending on the orientation of the neighboring protons with respect to the applied magnetic field, and thus its absorption is shifted up and down field. The signal is splitted into group of peaks. Now we see the different combination resulted from the orientation of the adjacent protons with the applied magnetic field and the subsequent multiplet observed. Look at here. If for a particular proton there is only one neighboring proton, then two different fields will arise from this integration. One field will be when this neighboring proton field is aligned with the applied magnetic field, and another one is neighboring proton field is opposite to the applied magnetic field. In that case, you will get a signal ratio 1:1. Okay, and when there are two neighboring protons, then three different fields will be found from this integration, and three different fields will arise how? When two neighboring protons aligns with the magnetic field, or one proton is aligned, one proton's magnetic field is aligned, another proton's magnetic field is opposing for that two combination, and another one when both the protons magnetic field opposes the applied magnetic field. In that case, signals will be observed at 1:2:1 ratio. It will be a triplet. Now, if there are three neighboring protons around a particular proton, then four different fields from the integration will arise, and four different fields how? All three magnetic protons will orientate aligned to this applied magnetic field. Another combination is two will be aligned, one will be opposing. Another combination, two will be opposing, one will be aligned, and other combination, all three protons magnetic field opposing the applied magnetic field. So total 4 fields arises from this integration, and you will get the quartet. Signal will be a quartet in the ratio of 1:3:3:1. Now we will see. In this molecule, this proton, there is no neighboring proton. Neighboring oxygen does not have any proton. So, this proton signal will not be splitted. It will give the single peak. Now, coming to this proton, there are how many neighboring protons? These 3 neighboring protons plus these 2 neighboring protons. That means total 5 neighboring protons. Signal of this proton will be splitted into 6 peaks. Now coming to these 2 equivalent protons. These 2 equivalent protons, how many neighboring protons are there? These 3 neighboring proton and this 1 neighboring proton. So signal of this equivalent proton will be splitted into 4. That means you will get the quartet. And what about these 3 equivalent protons? There are 2 neighboring protons. So each signal will be splitted into 3. That means triplet will be observed. And look at here. Here, these 3 protons, neighboring proton is only 1. So, signal will be splitted into 2, you will get the doublet. So, that number of peaks obtained after splitting, that will be equal to the number of neighboring proton plus 1. So, what we observe? Thus, a set of n equivalent neighboring protons will split the NMR signal into n plus 1 peaks. Now coming to some example. Look at here. In this case, these 3 primary protons of these methyl protons have only 1 neighboring proton. So its absorption peak will be influenced by this only one tertiary proton. And one tertiary proton means its signal will be splitted into 2. That means a doublet will be observed. So this doublet will be found. So all these things already I explained. If a particular moment the tertiary proton is aligned with the methyl proton, the effective field felt by the methyl proton increased, whereas field will be decreased when the tertiary proton align against the applied field. Already it was discussed. And then changes of these alignments are even, so that methyl proton absorbs slightly downfield for half of the molecule, which will absorb at downfield. The methyl protons which is experiencing the magnetic field where this tertiary proton is aligned with the applied magnetic field, those half methyl proton will experience more magnetic field, so they will absorb at downfield. And the remaining half methyl proton which will be experiencing the magnetic field where this tertiary magnetic field of this tertiary proton opposes the applied field, they will experience less magnetic field, so they will absorb at upfield. Thus, methyl proton signals split into two peaks. Now coming to this tertiary proton. Now, tertiary proton will be under the influence of three primary protons. That means splitting of the NMR signal will be done by these three primary protons. What are the combination for these three primary protons with the applied magnetic field? All three may be opposing to the applied magnetic field. Then that field strength will be minimum. So this tertiary proton which is experiencing this field strength, they will absorb at little higher field. And another combination is two primary protons opposing in the opposite direction of the applied magnetic field, and one is in the same direction. For these three combinations are there. Now, this tertiary proton which is experiencing this magnetic field, they will experience little higher magnetic field than the protons which is experiencing this magnetic field. So, they will absorb little lower field compared to this. Now, this is another combination where this magnetic moment of these two primary protons aligned with this applied magnetic field and one is opposite. So there are three combinations for this, and the tertiary protons which is experiencing this magnetic field, that means it is experiencing little higher magnetic field compared to this and this, so it will absorb little lower magnetic field or downfield. And this combination where all these primary protons are aligned with this external magnetic field, then tertiary protons which will experience this magnetic field, that means that is the strongest magnetic field, so they will absorb at this, then the tertiary proton will absorb at lower magnetic field or downfield. So finally, the signal will be a quartet in the ratio of 1:3:3:1. So, spin-spin coupling of tertiary proton with three adjacent primary protons gives rise to a quartet caused by the different alignment of three primary protons with the magnetic field, and this ratio will be 1:3:3:1. Now coming to coupling constant. Coupling constant is the distance between the center of two adjacent peaks of a multiplet, and it is denoted by J, and it is expressed in Hertz, and it is independent of the magnetic field, that is applied magnetic field, and the radio frequency. So the distance between the centers of two adjacent peaks in a multiplet is coupling constant or spin-spin coupling constant J. It is quoted in Hertz. It is independent of applied magnetic field or radio frequency. Now coming to the answers of the remaining question. How the neighboring isotopes are responsible for fragmentation. So all these things I explain that only is written here. Instead of single peak for one kind of protons, a group of peaks multiplet is observed in the PMR spectra. The splitting of NMR signals is caused by spin-spin coupling, which is indirect coupling of proton spin through the intervening bonding electrons. The field experienced by the proton is slightly increased if the neighboring proton, that is proton on the adjacent carbon atom, is aligned with the applied field, or decreased if the adjacent proton is aligned against the applied field. The absorbing proton thus may may experience each of the modified fields and its absorption is shifted up and down field. Thus, the signal is split into group of peaks. Now coming to the third question, what is the formula that gives the number of fragmented lines? Already you have seen a set of n equivalent neighboring protons will split the NMR signal into n plus 1 peaks. Fourth question, what will be the probable combination of the alignment of two same neighboring isotopes? Here it is proton with the direction of the applied magnetic field. Already we have seen. Say this is Hb proton and neighboring there are two Ha proton. Then this NMR peak of this Hb proton will be split into 3. 1:2:1 ratio of this combination. Both Ha protons are aligned with the magnetic field. One is aligned, one is opposite, and both are opposite. So we'll get the signal as a triplet in the ratio of 1:2:1. So this absorption of Hb proton is affected by the spin of the neighboring Ha protons. Two Ha proton whose spin will affect the applied field in Hb proton can give rise to 4 probable combination of the spin alignments, and the spin-spin coupling give rise to 1:2:1, that is triplet. Now coming to the today's question for the viewers. Today's question is, how many sets of non-equivalent protons are present in the given molecule? The molecule is this one. So we have to give answer how many sets of non-equivalent protons are present in this molecule. Mail your answer to malachemphilic@gmail.com, and in the mail you have to write your name, your affiliation, but that is not mandatory, then your place, and then you have to write answer of the viewer's question of riddle number 24, then write the answer. So don't wait, send your answer as early as possible. Thank you.